Fire it up there and drop it in some other pocket. Very good. It's great to be here, Simon. Thank you very much. It's a real pleasure, and that's showing up just fine. And great to be here. And certainly a lot of the work I'm talking about, as for everybody, is not possible without my students. There's a list of a number of them who have done the surface evolver work for me over the years. And the work over the years has been sponsored by a number of groups. And then there's other partners here, people, you know, the unfunded collaborations with some really great people there. I've had great pleasure of working both with Paul Conkis and Bob Finn on different things. Some exotic names in here like Blue Origin. And certainly, as I thought about it, the great enabler, of course, Ken Brecky with creating Evolver, which is hard to believe now that that's over 20 years ago. And in my end of the world, which is capillary fluid dynamics, I still run into people who say, what is this? What is this code you're talking about? So it's been around a while, but still not in great use. Oh, goodness sakes, what have I done with the video not running? Okay. You know, I always stay away from videos in PowerPoint, but today I thought I would. There, we can do that. Today I thought I would include some because they would be of great help. Oh, I don't know what that means. That's fine. Let's just go. Okay. The movie shows up if I run it for you guys and not for myself, so I will click on that, and we're in business. Okay, so I get to teach in a number of ways, including about capillary fluids, and here I am on the left with two of my undergrads some years back. Are we able to dim these front lights at all? There we go. Thank you. So that's their original experiment down there in that part there. I've also taught, I was looking at this, I've done children's television, talking about capillary work. I've taken Purdue students, brought them over here to Europe for a little tour through the continent on some stops on the Capillary Trail. That was very enjoyable. I've talked capillary fluids here and adjoining buildings in an advocacy role for the commercial suborbital industry that's emerging in the U.S. And here I am I'm in there with a couple of students at a launch site. New Mexico Spaceport America, north of Las Cruces. We had a student payload on this rocket pertaining to capillary fluids. So I get to do a lot of fun things, and this, talking to you guys being one of them. And when I looked at this, I thought, when I was looking back through years of surface evolver work, like Simon had suggested, it's frightening how simple the questions boil down to. Where is the liquid? And when will it stay there, or conversely, when will it leave? And so the work involves a lot of things that just come down to those questions. And Simon gave us a little introduction here. What I want to stress, I'm kind of an isothermal guy. Everything's constant temperature pretty much in what I work in. The second paragraph here, contact angle. Folks spend a lot of time, and I used to be involved in arguments about what's the proper definition of contact angle and this, that, and the other. And I realized, you know, contact angle is really a lie. It doesn't exist. It never exists. It's a macroscopic lie we tell about the results of this really complex, exciting molecular motion at the interfaces. And so every definition of contact angle is wrong, but I still use it. It's a tool we use. It's not physical. It's not a property of the fluid. And it's not a boundary condition, it's a result. It's a result of the energy densities, free surface energy density, wetted surface energy density. So that's my current little advocacy role in the community, is to push the notion that contact angle really is a result, and it's wrong, it's a lie, and I lie just as much as everybody else. So these two things come together and give us topics in existence and uniqueness of solutions, static shapes, capillary stability, critical wetting, and gravity and acceleration are involved too. And I also like to stress, I work a lot in what we call it zero gravity fluid dynamics. Gravity's still there. You're in an accelerating reference frame, but it's such a descriptive word, we keep using it, right? So it's an everyday phenomena. I don't work on exotic things, I tell people. I work on everyday phenomena, right? Space station's up there, going around and around every day. It depends on zero gravity fluid dynamics. Communication satellites are used constantly by industry, the television industry. Even if you say, I don't have a dish on my home, I have a cable. Well, but what you're watching on cable has come over satellites. And I do some fun work with industry on predicting the lifetime of the fuel in these satellites and when they're going to run out of fuel. And low gravity fluid dynamics are not just spaceflight applications, but here on Earth, as you know, the scale shrinks, the Bond number goes down, and with the increase in miniaturized medical instrumentation and devices that are coming out, it's becoming more and more of a earthbound application. The management of condensed water in the gas passages of certain fuel cell designs is growing as a capillary fluids problem here on Earth. So to me, it's an everyday process. In orbit now, capillary fluids experiment version 2, they're the second generation of CFE, is in orbit in space station, and Germany's capillary channel flow experiment is up there. And we'll talk more about, we have a fluids education being designed by my students right now. A couple of years ago, there was this prominent paper on gravity probe B, which was the relativity experiment. Long list of names there. No, I'm not on there. But this work, Gravity Probe B, was a many decades long program, and my friends in space physics still argue about whether it was worthwhile or not. But for me, it was really worthwhile because this started my work into surface evolver. Okay, so where is the liquid? Well, in the satellite, there's an artist's view of what the satellite looks like. In about that same orientation, you see here, this is a 2,500 liter dewar for liquid helium. And as you would expect, as the liquid helium warms, it boils, and so it becomes a liquid and vapor problem, which is not too bad for just a big dewar, but right down the core, on the axis of this dewar, is the actual experiment hardware. It's immersed in the liquid helium to chill it, and then this thing is spinning. The satellite is spinning about the axis of this tank, or it was. I guess it's probably still spinning. The mission is accomplished. It's in a polar orbit. It'll be up there more or less forever. And so here you see the column down the axis of the dewar, and the liquid and vaporous helium are outside of that, within the walls, but outside of that core rod, and it spins about the axis of this tank. Now, Ken Brackey worked first at this problem early in the surface evolver days. So I got involved in, I believe it was 1993, and Ken had solved this. And I'll tell you just a little bit more next slide or two about my involvement. But the picture here, if you start on the left, that black circle is the post, okay? We've taken a section cut through the tank, through the dewar. And the gray is the liquid, and that white there is the helium vapor balled up on one side of the post. And as the satellite spins faster, that bubble going from left to right spreads out around the post more. And one of the questions was, how fast does the satellite need to spin to create this axisymmetric state in which The bubble is axisymmetric, therefore the liquid mass center, which was really the topic of interest, the liquid mass center is on axis and there's no wobble in the spin. So given a certain amount of helium vapor on this post of a certain diameter, how fast does the satellite need to spin? And then also going back down in speed, if you start decreasing at what's the minimum spin rate that the toroidal bubble is stable at. So Ken did those, and for what was then Lockheed, and now Lockheed Martin, and he hasn't published it yet. I checked with him before coming over, but the ring blob demo in surface evolver is the toroidal bubble, so it's half the problem. I got contacted by Lockheed just because I had done some work there in previous years on satellite propellant management, and I really wanted to do a zero gravity experiment to test this for them, but they said no time and money for that, so we did a little 1G experiment. This is a tiny little model of that Dewar with room temperature liquid, and we ran our own surface evolver calculations, which included gravity straight down. And so whereas the on-orbit one has spin and surface tension, this one has spin, surface tension, and gravity. So it's a slightly more difficult task for evolver. And I dug up our, as my earliest original surface evolver model on the left there, that's the spherical topology bubble that has come around and the two ends are just kissing there. And here's a ancient black and white photo now of our experiment in that same condition. So the work for Lockheed was to confirm surface evolver. They said, hey, we like what this Professor Brackey has done for us, but how can we really depend on this? Let's do a quick test. And so we did that, and this is our old data. It's amusing to me to look at this 20 years later and see that we had 4 surface evolver results and many experimental results. In the era, that would have been really before the Pentium computer chip. And so computing surface evolver was slower than running an experiment. Now, of course, it's quite the other way around. Another task I did, so anyway, let me say that got me introduced to surface evolver, and at a time when in my career at Purdue I was looking for a new niche to fill without the need for spending a lot of money, and so the low gravity fluid dynamics then that's really when I got started into this, and I actually set evolver aside because it was too slow, too difficult, and then in '98 I picked it up again on a sabbatical in industry to solve a problem on orbit, and realized that was when I remember I had a 75 megahertz Pentium, and that was enough compute power to finally, I felt, do some really good 3D realistic work with evolver. So I've been riding it as my horse ever since. And one example is this infiltration of a square close packed sphere layer. Lev Slobozhinin, who was then at Case Western, I've tried to track down Lev since. I don't know where he's working now. It was wonderful to work with. And really, capillary pressure versus infiltrated volume was our work there. And at this point, this is one of the old movies that doesn't work with the new software, so I will very quickly bring up that movie for you. Yeah, I've been getting that. Don't worry about that. Okay, I've been getting that too. All right. Let me get the other player. This is exactly why I usually don't do this, but for this crowd, I really wanted the video. So this is what we put together, a quasi-steady study of this infiltration of a sphere layer. We'll run through it twice here. I'll explain it. Side view right here, liquid below, gas above. As you increase the amount of liquid into the sphere layer, what is the capillary pressure? And that's the plot on the left. So volume of 0 simply means you would have a flat layer at the equator of the spheres. And so this is all steady state results. There's no dynamics here. We just put this movie together after the fact. And that little red dot shows how we're tracing through the different branches of the curves on the pressure versus capillary pressure there. And again, Lev, really fabulous researcher and mathematician. I think if you've seen the big yellow Springer book of the low gravity fluid dynamics, the translation from Russian, Lev was one of the authors of that. And so he just ran wild with that, and that I wanted to share. That was another piece of work. I am really, there we go. Okay. So another question of where is the liquid came about from a phone call. Bill Lindsley of the U.S. Centers for Disease Control, National Institute of Occupational Safety and Health, or NIOSH, was studying how water droplets collect in lung passages. Their interest in occupational safety and health involved certain occupations in misty environments, mining, certain mines. I'm told that certain spray cooling processes in steel foundries give off a lot of mist that are inhaled. And if a lung passage is blocked, then oxygen and carbon dioxide are not being exchanged by the portion of the lung downstream of that. So they were interested in that. Lindsley had completed analysis of two axisymmetric solutions, and the non-axisymmetric solution being 3D, we needed to use evolver. So it has an analogy in orbit about gas bubbles in hydrazine fuel lines. And so the question was, how much volume will seal off a lung passage, and how does that depend on contact angle? And leading to other questions of what are the possible topologies of the solutions, how many different solutions are possible, what are they, and what are the pressures involved with that. The people in pulmonary health are very interested in the pressure in the passage. So we looked at this. Certainly the plug, the 1D case, you don't need evolver for. This is in zero gravity, so everything remains axisymmetric. There's a two-dimensional axisymmetric annulus. There's a 3D wall-bound droplet. You could think of a free sphere, and perhaps also a liquid bridge spanning the cylinder. So obviously the 3D case requires evolver. The 2D case we can do some interesting stability work with in 2 and 3 dimensions. The liquid bridge case, I'm sorry, the plug is a great test case, obviously, for our evolver. And we never did find any stable bridges in this work. When we were starting this was in the news also, that brought home another application of this type of work. And fortunately, in the 9 years since then, I don't think I've seen too many more notes of failed oxygen generators from bubbles. But we took all the bunch of assumptions here. It's a straight circular tube. I've had other students since this work on different topics, different variations of that. Rigid, impermeable, and smooth walls. The pulmonary people really don't like that, but that's where we start. Uniform contact angle and surface energies, fixed drop volume, we can add gravity later, and so on. And what do you get? Well, there's some example droplets in a circular tube for a range of contact angles. Even though I said early on contact angle is a lie, that's still how I talk about it, right? It's still descriptive. So this is in physics of fluids from some years back. Not just these droplets, but other geometries. I think the next slide is more examples here. cut the tube in half, there's an example droplet on the left, and there's an example annular sleeve on the upper right, and a plug on the bottom here. Black is the symmetry plane that's been cut. Now, these are all at the exact same contact angle and liquid volume. So there are cases where all three of these can exist and are stable, linearly stable. And so this is a fun illustration that way. I do not recommend, and I never bother with shading surfaces like this in Evolver, except when it's time to send it into the journal. This is a pain in Evolver. It's not made to be pretty, right? So fun things come out of this. You can look at what is the maximum droplet volume, and it goes from left to right, up, down, and back up again, which brings to mind then, well, what's going on? Why is it shaped this way? It turns out we found there are three mechanisms. On the small contact angle, those contact lines come around and meet on the top. In the midpoint there, it fills up to something like that cross-section shows, and then if you add any more volume, it's unstable. It pops to the plug. And then from about 135 degrees or so on up, it's really more like just inflating a balloon inside a tube. It just smoothly fills up the cross-section. So there's three different processes limiting the maximum volume you can have in a droplet, depending on contact angle. Overall results we put into a map like this. The parameter space is contact angle and volume here. And I say it's a map of existence, which are the lines, and of minimum energy, which are the shading. So let me explain. This, starting down here at the origin and coming up here to this peak and curving back up to K, that's the maximum droplet volume curve I showed you vertically on the previous slides. So that's everywhere to the left of this line you can have a droplet. To the right, it's not possible to have a droplet. Now from K over to B and down to D here, that's the minimum plug line, minimum volume plug. So a plug can exist stably everywhere to the right of that, and certainly out to the right it's only plug. You just keep getting a longer and longer plug as you move off to the right. This little sawtooth here, that is the range of existence for the annular solution. And this curve right here is actually the work of Slobozhinin, who I worked with on the sphere layer. In some other work, he did some very nice analytical work to spell out the limits of stability of the symmetric annular solution in a tube. And so the sawtooth is Lev's work that I added in. From my own Evolver work, I'd gotten, kind of this part here. I'd figured that much out. There's a lot of hunting and pecking here. We have thousands and thousands, many tens of thousands of Evolver solutions going into this. A student of mine, Bob Manning, put together ufluids.net. I don't think he's kept it running since, but it used the BOINC protocol from Berkeley that we had up to 7,000 volunteer computers around the world at night running Evolver cases for us. So we were able to rapidly build up far more data than we knew what to do with. So the black lines are the limits of existence, a maximum, a minimum, and then a double-ended existence for the annulus. The shading then is where in this parameter space each one is the minimum energy solution. Okay, this light gray, big light gray region is where the droplet is the minimum energy solution. The dark gray and to the right is where the plug is the minimum energy solution, and only in this little white triangle down here is the annulus, the minimum energy solution. So these lines break up the region, the parameter space, into regions where, for example, far away on the right here you can only have a plug. Down here you can only have a droplet. Here you can have a droplet or a plug. In here you can have a droplet or a plug or an annulus. Here only a plug or an annulus, and a little sliver down here apparently. It's hard to get good resolution at low contact angle, but apparently down here there's a little tiny region where only the annulus can exist. So that was a fun surface evolver study. Again, motivated by a question of where is the liquid and how big is it, and a number of conclusions coming out of that. The free sphere was really only the limiting condition for blowing up a 180-degree bubble in the tube. This has recently led into the fluids education experiment for the International Space Station. John Casito at North Carolina Ag and Tech State University is my co-investigator on this. Let me tell you about this part here. So NASA picked us almost 2 years ago. We're funded out of the National Laboratory Education Projects of International Space Station. There is no, right, Code U in NASA, the old microgravity sciences, was destroyed in the return to flight era from after the loss of Columbia. And so I've had no place to propose to. So for me, it's been getting to orbit by hook or by crook. And so I proposed to an education program. And I said, look at this. Every child has picked up soda pop in a drinking straw. That's capillary stability. Look, we can do a capillary fluids experiment and have a big educational impact. And they agreed, and it was really fun. So Purdue and NCAT have been supporting us also. This is really fun. This just hired the dean. My dean at Purdue hired one of our retired astronauts. Purdue's had 23 astronauts, and Dr. David Wolf is part-time now helping my undergraduate students specify and define and understand on-orbit operations, astronaut training procedures, and that sort. It's a real exciting time for the students. So this is a very small, simple, but unique capillary fluids experiment. Again, the STEM, in the U.S. we talk about STEM education as science, technology, engineering, and mathematics. So we're looking to impact STEM education in the school children, and our undergraduates are doing everything, almost everything, designing the experiment, doing the science. They're running Evolver for me, processing the data when we get it. They're prototyping the hardware, designing the on-orbit operations, creating astronaut training materials, and we're also developing the middle school STEM impact. And we've chosen a lot of hardware and operational choices. We've stolen them from the successes of the capillary fluids experiments of Mark Weisslogel. I got to help design 2 of those back in the early 2000s, and so that brought us risk reduction and schedule efficiency. Our money ran out in October, but they tell us when the government figures out what's going on, we'll have more money. This little thing here, this is the vein gap experiment, the prior work that we're stealing hardware and operational ideas from. That is very much a different fluids test. That is a critical wetting experiment there. I got to help design that with Mark Weisslogel at Portland State. So our program goals are to create this experiment, lead undergraduate students through a multi-year design, build, test program, and drive, create, and implement STEM activities for middle school and publicity and motivate students. Science goals are to test evolver predictions for ranges of existence, just like I was showing you with the circular tube, predictions of stability, predictions of overall shapes, generate video data for dynamics of transitions between states, which obviously you'll have to use a different code to use. Open foam looks like the best one now. Observe and learn. And to do these, we need to inject liquid into the tube in small controlled volume increments and withdraw it. So we've ended up going to a slender cone to bias the liquid in orbit to move to a desired position. There's this ball on top, which is large enough that it's lower energy for the liquid to wet the cone than it is the sphere surface. So we should keep the liquid in the cone, and we tried a number of things, and we're still running Evolver on more of this. Here's how these things come together physically in the payload. 3 blocks of acrylic form a block set. They're bonded together. You can see the cone right in here. And the students are doing this work. The actual flight hardware the students won't be making. We want really the utmost in professionalism and precision on the machining for those. But the students are doing great work. The tube actually ends up looking like this, and this is color-coded. The green area there is the science section. Yellow is a little extra length because we're not perfect in our predictions. That spherical cap up top, like I said, prevents the liquid from moving up because the liquid is lower energy in the cone. And here we have our anomaly funnel, we call it, where liquid will get where we don't intend it to be now and then, and the astronaut will be able to unbolt this from the workbench and, like in CFE, they centrifuge the experiment and drive the liquid down into here, and then there's a method for bringing it back to where you want it to be. Here's example student surface evolver work in elliptic cones. We have some circular test sections in there, some elliptical test sections, and so there is obviously the plug or the droplet up high. Here's the annulus, and there's the plug on the left. This is what the largely acrylic payload, transparent acrylic payload is coming out to look like. The test vessels are sketched there as solid bodies inside the acrylic, just to make it clear what they are, and there's some liquid reservoirs behind them. On the interior, 2 valves on each face to control which test vessel the liquid goes into, and then also to do the recover from anomalies. Aluminum base plate and top tray there. You see some hand grips at the top we're designing in. And this has been a real adventure with the students. There's the exploded view of the different parts coming together, a few little tricks for self-jigging, assembly, and this type of work. What I haven't had the students do is all the NASA safety paperwork. I've been managing that. I tell them, if we taught you about the real world, you'd all go off and be bartenders and waitresses. You have to ease them into that. So we're scheduled for launch early next year. We've been down to the space vehicle mock-up facility at NASA Johnson doing some fitting and camera positioning work. It was a real thrill for the students to be down doing that. We're mostly finished with Evolver. We are currently prototyping our valve designs, pistons and reservoirs and so on. STEM curriculum has been completed first generation. We're redoing it now to tie in more closely to what we now know will be on orbit. Awaiting word on continued funding, and this is how I teach at Purdue. This is Aero 418 Zero Gravity Flight Experiment, and it's just a real joy to be able to do all this. And here's some examples. Here's the Trevor down in the space station mock-up with our low-res, low-fidelity prototype and the camcorder that's going to be used in orbit, and looking at how does it all fit onto this maintenance work area. Student prototyping, hardware in the upper left. Upper right there, that's I have the great pleasure of working in Neil Armstrong Hall of Engineering at Purdue. He graduated from my department, obviously, long before I got there. There's a wonderful statue of him as a student, bronze statue of him as a student out front of the building, and so that was a North Carolina and Purdue get-together, and we had a team picture there. That's actually another astronaut standing in front of him in the blue blazer, Charlie Walker, flew 3 times in space early on. Here's what happens in space with liquids. This is a scale model of the Cassini spacecraft fuel tank here, and you'll see barely in this old low-res video, there's some sheet metal vanes inside that create corners, and corners create wicking, and that's what's done inside of a satellite fuel tank to keep liquid at the outlet of the tank. This is draining out the bottom, whereas just in the empty tank, you see the liquid splashes around and you vent gas for that. Well, that led into some work. That had been done, I mean, we're 50 years into flying satellites, half a century of space flight. And about a decade ago, there was still an unknown question about those vanes. They're not bonded to the wall in any way. They kind of come down to the wall and then stop short, so there's a gap. And we had been flying these devices for decades, and in my interest I said, well, how big of a gap is too big for it to act like a corner, and how small is small enough that this vein near the wall with a gap will act like a corner and have a critical wetting flows moving up this. So we got to look into this. I had a student, Young-Kung Chen, was my PhD student, built my first drop tower at Purdue, and he did wonderful student. I got him started on that and surface evolver. And then he also, he's the one who taught me how to do concus and fins analysis for critical wetting in a cylinder. So that was very good. And so we looked at a gap between a vein and a wall, and also other manufacturing imperfections, like the vein is not normal to the wall, it's skewed a little bit. And there's his surface evolver work for the geometry, the cross section on the left. There's a converged case with finite height. And then here's a case that's unconverged, non-converged, it'll just keep going up and up. If that name, Young-Kung Chen, is a little familiar, there's something out now called SE-Fit. He put together a user interface for Evolver for people wanting to do like propellant tank work. And so he did that now as a research professor at Portland State University. And so we now understand the physical limits of how such gaps can act like solid corners, both for critical wetting and then Young-Kung and Mark Weisslogel with capillary advance rates. Non-dimensional gap size, of course, is the important thing. Perfect alignment is not necessarily the case that gives you the strongest wicking, and blunt edges don't bother it. So Evolver still has unique powers, and I'm really happy to have been able to do so much with it. This is just a sampling. And many years ago I thought I would use Evolver until, well, as computers get faster, Moore's law kicks over a few more times. We'll just do everything with CFD and I won't bother with Evolver. You do start to realize that a surface mesh is always less computing power, less computing intensive than a volumetric grid. And everybody and their dog is running CFD codes now. I've met freshmen coming in at Purdue who in their high school, they wrote an Euler code for their science fair project. And I'm thinking, why would I want to try to catch up with them at this point in my career? And I've realized, yes, as computers become more powerful, we can attack more complex problems with Evolver. Larger parameter spaces through massively parallel computing, and not in terms of breaking up a given problem, but breaking up parameter space over many computers, since each Evolver run is not that long. We can attack larger ranges of length scales in one problem if you have more and more memory, and computing is more powerful. So, thus, I'm just going to keep running Evolver. It's my horse for a while now. I'll just keep riding it. And I really look to partner with people who are good at the other things that I'm not good at, okay? And thank you again for including me here, Simon. I really enjoy it, and I look forward to a delightful week with you. Thank you.
Other questions, comments? So you had the diagram of the sort of phase diagram of the three kinds of bubbles in the cylinder tube. The annular solution, of course, is an explicit delta surface of revolution.
Right.
So that was that strange shaped region where that existed or was stable.
Okay, right. If you restrict yourself to computing in axisymmetric space, there's a much larger range of existence. For the, let's say the profile would be able to, if I remember right, a nodoid, an unduloid, or a catenoid, depending on contact angle and volume. But if you look at three-dimensional perturbations, that's what Slobozhin showed you're restricted to.
Right. So the instability will break that.
Right.
But I'm just, the two curves, there was a sharp
Yes,
point.
yes.
So the two curves, when you approach that boundary, which instability, I don't know.
Oh goodness, that's a good question.
Turn to that slide, actually.
Yes, I could do that. I hadn't thought about that way. Mostly what I thought about was how lucky I am that Lev did that work and I could easily put that curve up there. Certainly, and the other thing too, okay, well, I would say you probably break at this point because from here the plug is the minimum energy and over here the droplet is the minimum energy. So you might drop to one or the other. But it's really, and I think one must be careful with Evolver. It's very easy to look at what's going on your screen and assign physical significance to changes, but Evolver is not computing motion. There is no d by dt in Evolver. There are no Navier-Stokes equations are not in Evolver.
I'm sorry, I forget who you said computed those curves.
Well, this shark tooth one, right? Lev Slobozhinin.
Right. So, but was he working with that kind of surface evolver simulation, or was he working with the mathematical?
Analytical, yeah. Yeah, actually, that annular, the kind of this part of the curve, and then going on up to point C, if you are purely a two-dimensional world with only two-dimensional perturbations, people had known that curve for a while, I think. Well, actually, I don't even know if that's the same curve with two and three-dimensional perturbations. We can talk some more, but yeah, there is right a minimum and a max for a given contact angle. There's a minimum and a maximum value of where the.
Presumably, the minimum is where then you start.
Yeah, it would look to me like the minimum, because it's in the light gray, is always going to become the droplet.
That's where you're going to start.
And between G and H here will be interesting, and H and above, I would expect it would become the plug. That's
It could be done analytically, is that the,
That's what I'm.
not just experimentally?
Right. Yeah, the minimum volume for the plug, that's just a high school geometry problem. And then the surface evolver gives us this, with enough work, you get the maximum volume for the droplet. We've since done this with collapsing tubes and toroidal tubes.
Yeah, I guess also when you had the fluid around the post,
Yes?
and you're asking when you go from the symmetric annular case and it becomes unstable, that also could be done analytically, that one.
Not by me. But, yeah, well, I suppose, yes.
I don't know.
I hadn't thought of that. There are a couple of, two of those PhD student names on there. They'd be upset with you that you invited their advisor to talk in a mathematical setting.
No.
You glossed over the idea of doing rough walls. Can you say a bit more?
Rough walls?
Yeah.
That's the type of thing now I think about with, as we get more and more compute power, that this is the type of thing that can become relevant. I've looked a little bit at rough walls. I've looked a little bit at, and that's where you need some really fine, to do a droplet of any magnitude on a rough wall, you need a lot of, that's a wide range of length scales, so you need a lot of memory, and that's certainly great interest now. Also, people doing, with some folks at Darmstadt working on textured surfaces, not physically profiled, but textured in terms of wettability. So a smooth wall with different wetting profiles and doing that. Super non-wetting surfaces and looking at, I still think something's wrong in Cassie and Wenzel limits, but it's not wrong enough to make a big deal out of. People say, well, you know, it's small enough we could neglect gravity, and my point is, yes, even when you neglect gravity, you don't have a spherical surface because of the boundaries. In many cases, you have aspherical constant curvature surfaces. Yes, you have constant curvature, but a sphere is a very special case of constant curvature. So I think there's work to be done there. I do, Simon and I started a sliding droplet discussion a decade ago, and In the years since then, I've convinced myself of both sides of that argument several times. So it'd be fun to look at that. But yeah, I'd love to work with people in different geometries and topics.
You said you never saw a stable bridge spanning the diameter, basically, of
Yes.
the cylinder, right? So is that always unstable to a symmetry break-in on sort of confluence? Or, I mean, I could also imagine breaking up into...
I guess, frankly, we could never get we could never get Evolver to converge on one in any way. Which, right, to say it can't possibly exist, you'd have to do a completely exhaustive search of the parameter space. So that's, I think, the somewhat of a weak language, my choice for a weaker language there. I don't think it exists anywhere. I haven't ever seen it, but we sure hunted a lot for it and never found it. But again, we could be missing a little region right here or something. You know, it's, until you check every point, you don't know. But I haven't seen found any, nor do I see any reason to think that that would be the minimum energy solution compared to these that have a lot more of the volume in contact or closer to the wall or wetting more of the wall. The bridge has very little wetted surface and a lot of free surface, and the wetted surface, at least for a wetting liquid, is what's reducing the energy. So it wants to wet more of the wall to reduce energy. So I don't, just intuitively that way, I don't see the bridge as an attractive option for the liquid.
I think maybe there are some recent theoretical results by Shane and his students on this sort of thing. Which ones might exist? I don't know.
That's fun.
Related to the Steck law.
Yeah, exactly, right? Yeah.
I have a question. So all the examples that you see in these very symmetric containers have the appropriate symmetry. I mean, they all have a plane of symmetry, right? All the equilibrium surfaces that you see. And you know, the case of constant contact angle, again, theoretically, they're pretty limited results outside of the case where it's a plane or maybe a spherical container where you can actually show that the symmetries of the boundary of the container are reflected in the surface. I'm just wondering, in the experiments, whether you ever encountered exotic equilibrium or
Yes, certainly. I've been working up, I happen to be working on a paper on that. All right, the droplet here, yes, has a left to right symmetry, but lacks the axisymmetry. Surface evolver, or the gravity probe B, you said it's symmetric cross-section, I should have a symmetric solution. No, you don't for many cases. Satellite propellant tanks within an axisymmetric container have 4, 6, or 8 sets of vanes, and you can find minimum energy solutions that do not reflect the symmetry of the vanes inside. And certainly Conkus and Finn's work in the 90s on their exotic container that ended up in a space shuttle experiment, showing not only asymmetric minimum energy solutions, but lack of uniqueness in those solutions. And it is a danger. It's in practical design, because one always says, well, you make assumptions as you're working and you're rushed, and whether it's a satellite or a ventilator tube in a medical instrument or something, and yeah, you get surprised. And going to orbits, going into weightlessness is a very good way to get surprised with liquid behavior we find.
Okay, let's next Stephen again. Thank you.
Thank you very much.